home stretch here. One more day off, and that's all you kids get before summer, huh? Oh, I feel so bad. Rough life. All right, here's what I got to talk about today. A little concept called tangent lines for a circle. Tangent lines. All right, I know you remember tangent from sine, cosine tangent, but this is a little bit different. What is a tangent line in a circle? Pretty easy. It's a line, hits the circle, one spot only. One spot only. Not two, not three, one only. So you guys can see my first diagram there. I have three tangents, A, B, E, F, and C, D. Why are they tangents? Because each of them hits the circle one spot only. All right, only hits one spot only. You can have infinite tangent lines for any one circle. All right. Now, more importantly, what about the diagram to the right there, my second diagram? Why are those four not tangents? Well, let's go through it. Maybe some of you can explain to me why I don't consider those tangents. Let's start with a line PQ. What's the problem? Hits in two spots. We got a name for that bad boy, but that's later on in the week. That's not a tangent, hits in two spots. What's the problem with RS? Doesn't hit at all. All right, well, VW does. Why wouldn't I consider VW a tangent? Hits exactly once.
It's not a line.
Yeah, it's not a line. Remember we call those a ray? And even if I say I extend it, what's going to happen? Twice. All right, so that's the problem there. And what about TU? Well, it's a radius and it's a segment. Okay, it's a radius and it's a segment. A tangent needs to be a line. All right, a line. All right, so that's a tangent. Hits the circle in exactly one spot. All right, well, I also have what's called common tangents. When you have two circles, if I have two circles, a common tangent is a single line that I can draw that intersects each circle in one spot only. Here's what I mean. Take a look at my first diagram with the interlocking circles. Where can I draw a line in that will only intersect each circle in one spot? Here's one of them. See what I mean? Hits it here and hits it here. One spot each. I'm claiming there's two. Do you see another one? Because I'm claiming there's two common tangents in this diagram. Do we see the other one? Right down below. Right here. One spot on that circle, one spot on the smaller circle. Okay? So that's what a common tangent is. I have two circles. Can you draw a line that's tangent to both at the same time? All right, second diagram. I'm claiming there's four. Where are they? Ooh. Can you find all four? I'm claiming there's four. Can you find all four here? First two, very similar to my last question here, right? One on top, one on the bottom. What about the next? Where's the other two then? What's up, Maeve?
Diagonal.
Yeah, diagonal, kind of going diagonal between the circles here. So here's another common tangent, and here's your fourth one right there. Perfect. Got to hit each circle one spot only. Any questions from you guys in class, you guys at home? I don't know about anybody else, but my Google Meet is just going crazy here. I don't know, anybody at home is having that issue? Like my camera keeps going in and out. All right. Next one, I'm not claiming anything. In this next diagram here, I'm not claiming, I'm not claiming anything. Can you find how many tangents should I have? Common tangents. How many should I have here? Anybody suggestions? How many did you find? Kyle? Three. Yep. Should have three going here. Here are the three. One on top. One on the bottom. Many of you probably got those two. And then where's the third one? Right through where those two circles are touching. There it is. And then my last diagram. The circle within a circle. Just touching. Only one common tangent. Yep. Tonight on homework, is it possible to have zero? What would your diagram look to have zero common tangents? Think about that one. You'll answer that tonight on homework. All right, any questions? All right, now to our first theorem, our first fact about tangents today. Here's what I need you to do. I need you to draw a circle for me right next to this theorem. Draw a circle and any line, make any line tangent to it. Okay, make any line tangent to it. Remember, there's infinite tangent lines you can draw for any one circle, so just make one line tangent. All right, can you please mark the point where it's tangent? Wherever it's tangent on the circle, mark that point. All right, can we stop calling it that point now? Let's actually put a name to it instead of calling it that point that it's tangent to. I know you'll see these mathematicians were just nuts way back in the day. That point where the line is tangent to the circle is called the point of tangency. How about that, kids, huh? Pretty creative on those guys or ladies back in the day. All right, point of tangency. That's where the tangent line intersects the circle. Now what I want you to do, put a center point in your circle, please. Put a center point. Here's your first theorem of the day. Please draw a radius connecting the center to the point of tangency. Connecting the center to the point of tangency. If you have this, if you have a radius that is drawn to the point of tangency, those two are perpendicular. If a radius is drawn to a point of tangency, both the radius and the tangent are perpendicular, meaning they form what? There we go. And there it is. Radius drawn to a point of tangency, those two are perpendicular, which means they create a right angle. All right? All right, so let's use that theorem and go back to Algebra 1 now. How can I use this theorem in some of these algebra problems? All right, assume these lines appear tangent, are tangent, center C. I got the central angle's 58. What about angle X? Well, now that you guys know that theorem, you should be adding on your own angle measurement right now. I see a radius that's going to the point of tangency. I know those two bad boys are perpendicular, so I am very confident in putting a right angle there. That's what the theorem says. Those two are perpendicular. Perpendicular lines form right angles. Think you can find X pretty easily? It's in a I'm not going to ask anybody here, but it's in a triangle, right? 180 degrees. So I got 180 total, minus the 90 I just found, minus the 58 I'm given. And that should be a whopping 30. I'm looking because I messed this up, believe it or not. 32 degrees, first period. All good? All right, where else could I use it? Oh, somewhere else giving me a right triangle. Okay. All right, AB is tangent to circle C at B. Perfect. So CB is a radius. So that tells me at angle B, those two are perpendicular, making a right angle. So I have a right triangle, and you're working with the sides. You're working with the sides of a right triangle. Help! Help! How can I find X? Give me a device that can find X in this right triangle. And how about this? I just landed on this first period today, the new generator, giving me a nice bold number now. I know, and these little things impress me. 16, here we go. Kyla, what you got a device for me to find X? Pythagorean Theorem, good. A squared plus B squared equals C squared. Good job. All right, help me out. What are the two legs, A and B? How long? How long? 12. Lucas, here we go. How long? Give me the two legs in this right triangle.
AB and BC.
Okay, what are they labeled?
Sorry, I can't really see.
X squared and 8 squared. There we go. How about the hypotenuse in this diagram? Be careful now. 16, Kyla, going back to you. What's the how can you label the hypotenuse here?
X plus 2 in parentheses squared.
Perfect, perfect. The hypotenuse is x plus 2, but when I show you I'm about to square it, I put it in parentheses squared. And this is going to make my blood pressure rise. X squared plus 64. Act like you're in honors, please. It's not x squared plus 4. It's not x squared plus 4. Remember, it's x plus 2 times itself. How about a little FOIL double distribution there, kids? Oh, x squared plus 4. Get out of here. That's just an embarrassment to the math community and your family. So FOIL, double distribute, combine your like terms. I'm hoping you guys get x squared. Add the 2x and the 2x to get 4x. 2 times 2 should give you 4. So that's what you end up getting when you multiply those two. All right, we're asked to solve for x. Hey, I see an x squared on both sides. So no matter which one I move over, what's going to happen to them? See ya! They're gone, right? I don't care if I move the one on the right over or the one on the left over. They will cancel each other out, and I'll be left with 64 equals 4x plus 4, and you're darn right, everyone can do that. And hopefully we get x equals 15. I'm not even going to ask. 15. So using that theorem gave me the right angle. And then since I was working in a right triangle, I could use Pythagorean Theorem. All right, help me with 3 now. First thing I want to know from someone, where is the right angle in my diagram? Name the right angle here. 8. Here we go, going home. Ryan, name the right angle. Where is it?
Angle CBA.
Good job. Wherever the radius and the point of tangency meet, I have a right angle, just like I did in problem 2, Pythag time. Except this here, I didn't label all the sides for you. I didn't label leg CB, but can you find, maybe? Can you find it? Maybe? 1, 3, here we go. Sophia, can you give me the measures of the 2 legs in this right triangle?
3x.
Okay, x squared, can you tell your classmates how you know CB was 3?
Because the radius is labeled as 3 and
Yep.
the hypotenuse.
Good. So any radius would also be 3, including CB. Yep. And then the hypotenuse, we got 10 squared here. Everyone's all good. All right, here you go. I didn't have any rounding direction, so I'm just going to leave it in radical form here. If you subtract 9 over, you get x squared equals 91. X, take the square root of both sides, is the square root of 91, and I'll let you know, save us some time, you can't break that down. No perfect square goes in the 91, so that's broken down as far as it can be. So I'll just take that. All right. Any issues? All right, I know some of you guys are getting ahead and doing number 4. I'm actually going to take a shortcut on number 4. All right, so I don't have to factor on this one. And I'll show you my shortcut here in a second. All right, I get it. There's my angle at CBA. Got it. A squared plus B squared equals C squared. All I need from somebody is, what are the 2 leg measures on this one? What are the 2 leg measures? 6, Caroline, what are the 2 leg measures on this diagram?
12 and then 9.
9, good. CB is a radius, and I know another radius is also 9 here, so that means that's 9. Now, here's what I'm going to do, guys. Watch what I'm going to do. And many of you might put x plus 9 all squared, FOIL, double distribute. That's fine. And then you'll have to factor. I have no problem with that. I'm just going to take a shortcut. Watch what I'm going to do. I'm actually going to find the length of the entire hypotenuse here, CA. And then how can I find x when I find that value? Okay, just subtract 9 from it. Okay, so yes, I am taking a short. It's correct, though. Okay, Nice little shortcut so we don't have to factor. You're welcome. So I'm going to find the length of the entire hypotenuse and then subtract 9 from it. All right? So I get 144, I get 81, I get 225 equals c squared. I get 15 equals c. C, that's the hypotenuse, not x. We just discussed. If I'm going to find x, I'm going to take 15 and subtract 9 from it. So 6, which you would still get if you set equal to x plus 9 all squared. You would just had to done a little extra multiplying and factoring. Maybe rejected a negative as well. All right, it still would have worked. You still would have gotten 6. All right, any issues or questions with if I draw a radius to a point of tangency, it's perpendicular, forms a right angle? Any questions with that? Because that's the first half of today. Second half right now is coming up with a new theorem. Questions from you guys at home? Anybody at home have any issues? All right, well, I made it easy on you. I just gave you this last theorem, that the radius is perpendicular to the tangent at the point of tangency. I gave that to you. I'm going to make you work for the next theorem now. All right, I'm going to make you work by helping me complete this proof. Okay. I am asking you to show me why tangent BA and tangent BC are congruent. Okay? There's a theorem that says why they're congruent, but we're going to prove that theorem right now. All right. So if you're going to ask me BA congruent to BC, we've been down this road before. What am I going to ask you to do first before I show the segments are congruent? Prove the triangles. So I can do a little CPCTC at the end. So that's what I need everybody's help with right now. Get me those two triangles congruent by one of the 5 methods. And it is good. I'm just warning you guys, it's going to be a tough one. All right, this one's going to be a tough one. All I gave you were BA and BC are tangent. That's it. I didn't give you any sides. I didn't give you any angles congruent. That's on all of you right now as a class to get this job done. All right, let me open it up. Anybody see anything you can tell me is true about this diagram? Let's start it up. 14. Ellie, anything you see is true here?
Radii AO and OC are congruent.
Nice. Good start. I like it. I got AO congruent to CO. Good start, Ellie. In a circle, gotta have that piece. Gotta have that piece. In a circle, all radii are congruent. Good job, Ellie. I got a pair of sides. You can thank Ellie. Pair of sides. All right, let's keep going. Anything else you know is true in this diagram? We got the radii congruent. 12, here we go. Lucas, anything else you know is true in this diagram?
BO is congruent to BO.
Got to throw that bad boy in there, right? BO congruent to itself. Good work, guys, so far. This isn't that bad. So I got a reflexive side. 2 sides. 2 sides, guys. 2 sides. Good. Oh. Anybody see anything else that's true in this diagram? What's up, Sean?
Angle A and angle C are congruent.
How do you know that?
They're both right angles.
Okay, well, here you go. Here's what Sean's saying in class. Angle A and angle C are congruent because they're right angles. Okay, I got to keep backing up here because I'm not ready in the proof right now to say at step 4, A and C are congruent. Okay, they're congruent because they're right angles. How do you know they're right angles?
Because radii that pass through the point of tangency are perpendicular.
Okay, that's what the theorem we just went over says. The radius and the tangent are perpendicular. It said nowhere in the theorem that they form a right angle. So what I need to write right now in the proof is radius AO is perpendicular to tangent AB. And the same thing is true on the other side. Radius CO is perpendicular to tangent CB. Okay? The theorem says they're perpendicular, not that they form right angles. And what's the theorem say? Radius drawn to, where's it got to be drawn to, the radius? The point of, not anywhere on the tangent. Radius drawn to point of tangency is perpendicular to the tangent. And I'll write line in there too. It's perpendicular. I know that's a mouthful, but that's what the theorem says. There's no not too many abbreviations there. Radius drawn to the point of tangency is perpendicular to the tangent line. Now can you tell me you have right angles? Yeah, this is old school, isn't it? Angle A and angle C are right angles. Old school, right? Perpendicular lines form right angles. Uh-oh. We think we're good to go, right? Because you guys gave me 3 pairs. You gave me 2 sides and an angle. You might want to look where that right angle is. Is this side angle side? No, absolutely not. Those right angles are not in between. And we better not be writing down SSA. Are you kidding me? At this point in the year, you're going to write SSA, even though some of you did on the quiz. Just throwing that out there. So what's the deal with it? It's not side angle side. There's no such thing as SSA. Do I need to find more? Do I, Kyle?
Yeah, you do.
Do I? What type of triangles do I have up there?
Right.
I have right triangles, don't I? And isn't there a specific method out there for right triangles only? What's that specific method for right triangles only? What is it? H. What's the H stand for? Which is your reflexive side. And L, which stands for leg, which are the radii. So yeah, this is going to be HL. But not right now. If you're going to use HL, way back in the day, I know I'm going so far back. Oh, I feel so bad, honors kids. Do you remember what I need to state before saying the triangles are congruent by HL? The triangles are right triangles, yeah. Right, because that's only for that method. So I need to tell you I got some right triangles. So that's what's coming up next. Oh, I'm so sorry. And no, you do not need to tell me in an HL proof the right angles are congruent. You can, it's not wrong, but you don't need to. So triangle AOB and triangle BOC are right triangles. Anybody remember the old reason? How do I know they're right triangles?
Right triangles.
Because they have right angles. And then we should be on our way now with the next 2 steps. Now you can say they're congruent by the HL method. And then those 2 segments are congruent by little CP, CTC. I got HL. Oh, we just came back from break and he's doing an HL proof. Madness. Nope, it's just called sucking it up. BA congruent to BC. CPCTC. All right, well, great job. All right, that was a tough one to throw that on you. First proof coming back from break. What did we just prove? We just proved the theorem that you don't have to do this proof anymore. You can just tell me BA is congruent to BC because of this theorem that you guys just proved true. What are BA and BC? Other than segments, they're what? Tangents. Everyone see that they're tangents. Two tangents, and they're both drawn to where? The same point, point B. So here's what the theorem says. Let's put that all together now. Two tangents drawn to the same. Now I'm going to put in an extra word here instead of just putting to the same point. To the same external point. What do I mean by external? Where's that point have to be? Darn right, outside the circle. Two tangents drawn to the same external point are congruent. That is what you guys just proved here. Any two tangents that are drawn to the same external point will always be congruent. Oh, yep.
Based on how we proved that specifically, because aren't BA and BC drawn to different points in the circle?
They're both drawn. AB and BC are both drawn to point B, aren't they? Tangent AB and tangent AC, or tangent AB and tangent CB intersect at point B, the same point.
I was thinking point on the circle.
No, it's got outside the circle. Outside the circle. Okay? To help you guys remember this theorem, many students in the past refer to this theorem as the party hat theorem. Anybody? What?
Aren't AB and BC segments?
You could write in tangent segments if you wanted to. Yes, they're part of
Didn't you
tangents.
say that tangents have to be lines?
They do, but here's the thing. I could continue these on, and those parts, AB and BC, would be congruent. Okay? So I could modify that and say two tangent segments drawn to the same point. Yes.
No, I just in the definition said lines.
Yeah, it's part of a line.
Yeah.
Yes. Okay? But the ones that are drawn to the same point are equal. Radhika.
If you got a proof like this again, could you just use the theorem?
It's a two-step proof.
Okay, so we don't have to do
Given, and then this is why, we just went through why it's true. Yes. Correct. Yep. Now, I'm blowing up my steam here. Party hat theorem. We're good? Yeah. Maybe what's that little chin strap they have there? Goes over. No, you cannot put party hat theorem in your proof, by the way. All right, some kid. What's that?
the little pom-pom at the top.
Oh, sorry.
That'll be the point. There we go.
There you go. Yeah. Okay, we're all good. As creepy as that is. All right. All right, where do I use this new party hat theorem? Here you go. When I have a polygon circumscribed a circle, around a circle. All right, if you have any type of polygon, triangle, quadrilateral, whatever, around a circle, this comes into play. This theorem we just proved comes into play. Watch. Take a look at number 1. It says, find the perimeter of each polygon. Do you guys see tangents going to the same external point? Here you go. Here's the first two I see right here. So according to my theorem, those two are congruent. I see another pair, don't you? Going to the same external point. Right here. Those two are congruent. And then finally, you see the third pair? These two smaller segments here. All these three pairs are congruent to each other because of the theorem. Two tangents drawn to the same external point are always congruent. And I'm hoping now it makes this problem easier. Well, if that's 4 and these two are congruent, that'll be 4. These two are equal, so that's got to be 5. And then these two smaller ones are equal, so that's got to be 3. So perimeter, all sides added up of the triangle, 7, 8, and 9. (24 centimeters). So this is where I'm going to start using this theorem, is when I see a figure circumscribed around a circle. Because I make, yep.
How come something like the line that says 4 centimeters and 3 centimeters, like that whole line, isn't congruent with the whole other lines? Why is it only the part of it?
Say that again?
Why is it that only part of the lines are congruent to the part of the other line? Why isn't the line on the left also 7?
Okay, it's just going to be from the point of the segment that starts at the point of tangency to where they meet. That's what we just proved. Not the full tangent segments. It's just from the point of tangency to where those two meet. I see what you're saying, but to get more detailed with the theorem, it starts from the point of tangency to where the two meet. Those are the two pieces that will be congruent based on that theorem. Not the full ones there. Okay, it's got to start with the segments that are congruent have to contain the point of tangency as one of their endpoints. Better definition there?
I think so.
Okay. So going over here to number 2. Now I see, all right, here to here, here to here. Those two will be congruent. And then from this point of tangency down here to here, those two will be congruent. And then the smaller ones will also be congruent. There we go. So knowing that information, go ahead right now. Hopefully are you working your way around the triangle? 6, 6, well that was 9, so that's got to be 3, 3. Whole side was 8, so that's got to be 5, meaning this is 5. So what do we have? 9, 8, and 11. So the perimeter will be 28 inches. Questions, comments? These last two are just randoms. Okay, don't think it has anything to do with tangent segments drawn to the same external point. These two are just random. See what you can do with your circle facts.
What is the 50 pointing to?
The 50 is pointed to that angle, the bottom right-hand angle in the triangle. That is what the 50 is pointing to. All right, let's start with number 3. I really don't want to, I want to work together as a class on this, but I don't want to just tell you what to do either. So we got to find angle X. I know the central angle is 130. Can you add in anything else based on our discussions today? Can anybody add in anything else based on our discussion today? Maeve?
That the two lines are congruent and that they're right angles.
Okay, I have a radius drawn to the point of tangency. Don't forget already. I have right angle here and a 90-degree angle over here. All right, good start. Let's keep climbing towards X now. Now I'm going to have to get away from circle facts to go to a totally different geometry fact here. How many sides in this figure here? 4. Anybody know what all the angles add up to in a 4-sided figure? 360. And you know how many already? You know 3 out of the 4. Okay, 360 degrees in every quadrilateral. Now, somebody said this in my first period class, and I don't know if anybody was ready to chime in. If you were going to say opposite angles are supplementary in a quadrilateral, but remember that's got to be in this. It works by coincidence on this one, but to use that theorem, the polygon needs to be the quadrilateral needs to be inscribed inside the circle for you need to use that theorem. And then how about number 4? Anything you want to tell me about the triangle there on number 4? 50 is pointing to this angle right here. That's 50 degrees. Anything you guys at home are seeing for that one? Anything else I could add into my diagram, you guys at home? that you know is true? Nothing from you guys at home? Somebody's got to know something. You want to take it, Emma?
The radii are congruent, so that's like an isosceles triangle.
Yep. Here's what Emma just said in class. All radii in a circle are congruent. Now I have an isosceles triangle. Keep going.
So that makes the other angle 50 degrees.
Yep. The angles across from the sides are congruent, so that makes that 50 degrees and makes this an easy problem now. 180 minus the two 50s. Now I'm looking at 80 degrees. Yep. Bottom of your page. Let's really work at problem number 35 tonight. I gave you a huge hint there what to do with that quadrilateral in number 35. Okay, you'll be fine. Make it into a rectangle and a right triangle somehow. All right, and get after it. All right, guys, I will see some of you guys tomorrow in class. Have a good night. Behave. Be smart.